You are alive in a universe that once had no stars, no planets, no atoms heavier than helium, just dark, silent hydrogen gas. And then, something impossible lit up the darkness. Recently, the James Webb Space Telescope, JWST, may have finally caught the light from those very first monsters. Stars so huge and so hot that, until now, they were only theory. Astronomers call them population 3 stars, and if the interpretation is right, what JWST saw 13 billion light-years away rewrites our understanding of how everything, including you, began. 1. A signal that shouldn't exist. March 2024, a team of astronomers is combing through JWST data when one spectrum on the screen makes them stop cold. The light comes from a tiny, distant galaxy labeled LAP-1b, so far away that its photons have been traveling for 13 billion years before they hit Webb's mirror. We're seeing it as it was when the universe was only about 800 million years old, just 6% of its current age. Already that's impressive, but the details of the light are what really shock them. The spectrum shows enormous numbers of high-energy photons, far more than ordinary stars could produce. Temperatures equivalent to stars with surfaces near 90,000 K, nearly 10 times hotter than our sun. And, most importantly, a near total absence of heavy elements. No clear signatures of carbon, no oxygen, no iron, almost no metals at all. Just hydrogen and helium, the original elements from the Big Bang. Modern stars are recycled. They're born from gas already enriched by previous generations of stars. Carbon, oxygen, iron, and more. That's what we see in their spectra. But this galaxy seems pristine, untouched, primordial. For decades, theorists had predicted such stars, the first generation born from pure hydrogen and helium clouds in the early universe. They called them population 3. They should be incredibly massive, tens to hundreds of times the mass of the sun, extremely hot, so hot that they flood space with ultraviolet light, extremely short-lived, burning out in just a few million years. Everyone thought they'd be almost impossible to find. They live fast, died young, and their light is faint and stretched into the infrared by the expansion of the universe. And yet, here's a spectrum that looks exactly like the computer simulations said population 3 stars would look like. But how did JWST even see a tiny, faint galaxy so far away in the first place? 2. Using gravity as a telescope. Over a century ago, in 1915, Albert Einstein predicted something wild. Massive objects don't just pull on things, they curve space-time itself. Light, always traveling in straight lines through space-time, will follow those curves. Around something extremely massive, its path bends. This effect is called gravitational lensing. Put a huge mass between us and a distant galaxy, and that cluster acts like a cosmic lens. It bends the light from the background galaxy, it magnifies it, it can stretch it into arcs or even split it into multiple images. The heavier the cluster, the stronger the lens. For decades, astronomers saw this lensing, but our telescopes weren't sensitive enough to fully exploit it. The ancient galaxies behind the lenses were just too faint. Then came JWST. With its 6.5-meter mirror and powerful infrared instruments, JWST can see extremely faint, red-shifted light, photons that started as blazing ultraviolet from young stars and arrived here as gentle infrared after 13 billion years of cosmic expansion. Yet even JWST needs help to see the faintest objects from the dawn of time. So, astronomers use a trick. They point Webb through massive galaxy clusters that act as gravitational lenses. The cluster provides a natural zoom. JWST provides the sensitivity. The galaxy that contains these candidate population 3 stars, LAP-1b, sits behind such a cluster. That cluster is known as MECS J0416. It lies about 4.3 billion light-years away and is actually a system of 2 colliding galaxy clusters, each containing hundreds of galaxies, vast clouds of hot gas, and enormous amounts of dark matter. This entire structure weighs roughly 1,000,000 billion times the mass of the Sun. All that mass is what bends space-time hard enough to act as a powerful lens. Hubble previously imaged MACS J0416 as part of the Frontier Fields program and revealed arcs and stretched background galaxies. Detailed modeling of how those arcs are distorted let astronomers map the cluster's mass and predict where magnification would be strongest. Right behind this cosmic wreck of merging galaxy clusters sits LAP-1b, perfectly positioned. Thanks to the gravitational lens, LAP-1b's light is magnified by about 100 times. Without it, JWST would barely detect it. With it, we don't just detect the galaxy, we can split its light into a spectrum and study its physics in detail. Einstein's curved space-time becomes a telescope, and what it reveals is extraordinary. 3. A baby galaxy in a changing universe. LAP-1b is tiny compared to modern galaxies. Its total stellar mass is only a few million times that of the Sun. By contrast, the Milky Way holds hundreds of billions of stars and weighs in at around 1 trillion solar masses. In Webb's images, LAP-1b doesn't look like a clean spiral or smooth ellipse. Instead, it's clumpy, made of small, bright knots, intense pockets of star formation. Even more important than the picture is when we're seeing it. We're looking back to a time when the universe was just 800 million years old, still emerging from the cosmic dark ages, in the middle of a crucial transition called reionization. After the Big Bang, the universe was initially an opaque plasma. About 380,000 years later, it cooled enough for electrons and protons to combine into neutral hydrogen, and light finally could travel freely. That relic light is the cosmic microwave background. But even though light could travel, there were still no stars. Just dark, neutral hydrogen-filling space. This period is called the Cosmic Dark Ages. During that darkness, dark matter began clumping under gravity, forming invisible halos. Ordinary gas, hydrogen and helium, fell into those halos. The gas heated as it collapsed, then slowly cooled. The problem is, with only hydrogen and helium, cooling isn't efficient. There are no heavy elements, no dust grains, no complex molecules to radiate away heat efficiently. This is crucial. How gas cools determines what kinds of stars form. In the modern universe, gas clouds have metals and dust, which allow efficient cooling, fragmentation into many small cores, and formation of many low-mass stars, like the Sun. But in the primordial universe, the gas can't cool well. It remains hotter, under higher pressure, and doesn't fragment easily. So instead of many small stars, the collapsing gas tends to form a few very massive stars. This is why theorists predicted that the first stars, population 3, would be giants, 30, 100, even 300 times the mass of the Sun. And because massive stars burn their fuel extremely fast, these first stars would live only a few million years before dying in titanic explosions. LAP-1b sits right in this transitional era. The universe is starting to light up. Neutral hydrogen is being ionized by the ultraviolet radiation of the first stars and galaxies. Inside LAP-1b, the suspected population 3 stars are so hot, around 90,000 K, that they flood their surroundings with ionizing photons. They carve out a bubble of ionized hydrogen in the neutral universe. Their light carries a signature, strong emission from doubly ionized helium, He2, combined with an astonishing lack of heavy elements. That's exactly what JWST sees in the spectrum. 4. Why these stars are so different. To understand why population 3 stars are so extreme, we have to compare them to stars like our own. Our Sun has this following feedback. Mass, 1 solar mass. Surface temperature, nearly 5,800 K. Lifetime, 10 billion years. It burns hydrogen gently in its core, slowly converting it into helium, stable for billions of years. A population 3 star with 100 times the sun's mass is a completely different beast. Mass 100 solar masses, luminosity up to 1,000,000 times that of the sun. Surface temperature nearing 80,000 to 100,000 K. Main stage lifetime only 2 to 3 million years. Because fusion in the core is extremely temperature sensitive. Higher core temperature plus higher density equals insanely fast reaction rates. The star burns through its hydrogen fuel thousands of times faster than the sun. The star is also almost completely metal-free. That low metallicity makes the gas more transparent to radiation in some ways, changes how radiation pressure works, and lets the star grow to huge masses before equilibrium. The result is a monstrous, unstable, hyperluminescent 1. Big picture. Object, the supermassive black hole at the center of the Andromeda Galaxy, M31. Mass, about 100 million times the mass of the Sun, much larger than the Milky Way's approximately 4 million solar mass black hole. Behavior, extremely quiet and underfed. Not a bright, violent quasar, but a dark, gravitational anchor shaping the inner galaxy. 2. Andromeda itself. Distance, about 2.5 million light-years away, the most distant object you can see with the naked eye as a faint, fuzzy patch. Type, large spiral galaxy, bigger than the Milky Way. Structure, bright central bulge of old stars, spiral arms with blue, young stars and star-forming regions. A halo full of faint stars and stellar streams, leftovers from small galaxies Andromeda has swallowed. Local group. Along with the Milky Way, Andromeda is one of the 2 dominant galaxies in our small gravitational neighborhood. 3. The black hole as a quiet anchor. Sits at the very center of Andromeda's bulge, acts like a massive gravitational weight, controls the motion of stars very near the core. It helps stabilize the central region over billions of years. Not tearing everything apart. Most stars are in stable orbits. Space is mostly empty, so actual collisions or being eaten are very rare. The black hole is invisible itself, but revealed by how fast nearby stars move and how their light is Doppler shifted. 4. How astronomers found it. They never saw the black hole directly. They inferred it from stellar motions. Stars near the center move much faster than gravity from visible stars alone can explain. The closer the star, the faster it orbits, points to a very dense central mass. Light profile of the core. Brightness rises sharply toward the center, which means many stars packed tightly plus extra hidden mass. Double nucleus. High-resolution Hubble images showed 2 bright peaks at the center. This isn't 2 black holes, but a disk or ring of stars whose orbits and perspective make it look double. Multi-wavelength observations. Infrared sees stars through dust, confirms high stellar speeds close in. Radio, faint, compact source, weak emission from tiny amounts of infalling gas. X-ray, very faint glow, rare hot gas, very low feeding rate. Simulations, models of star motion only match observations if a supermassive black hole is included at the center. 5. What it's like near the black hole. The region around the black hole is mostly empty, surprisingly orderly and calm. Event horizon physics. As you approach, gravity curves space and slows time from a distant observer's view. At the event horizon itself, nothing special is seen locally. There's no glowing surface. Tidal forces. For a black hole this massive, the tidal stretching at the horizon is relatively gentle. Infalling stars would be torn apart only deeper inside, not far outside the horizon. Feeding. Very little gas loses enough angular momentum to spiral in. Rare snacks, like small clumps of gas, create faint X-ray or radio flickers, not big flares. 6. Star clusters and the double nucleus. Near the center are dense star clusters, like compact cities of stars orbiting in the black hole's gravitational landscape. They remain stable because their own gravity holds them together strongly enough. The double nucleus is a disk or cluster of stars in eccentric orbits around the black hole. From Earth, their arrangement produces two apparent brightness peaks. These structures show the black hole's influence is strong but not destructive. The central region has been stable for a very long time. 7. Andromeda versus the Milky Way's black hole. Mass. Milky Way, Sagittarius A, approximately 4 million solar masses. Andromeda, approximately 100 million solar masses. Activity now, both are quiet, underfed, and dim. Observational difference. We're much closer to Sagittarius A, so we can track individual orbits over years. Andromeda's black hole is farther and bigger, easier to detect by population behavior than by single stars. Environment. Milky Way center has young, massive stars and some gas. Andromeda's core is more dominated by old stars and a settled bulge. 8. The future. Milky Way and Andromeda merger. Andromeda is moving toward the Milky Way about 100 kilometers per second. In billions of years, they will gradually merge. Dark matter halos overlap first. Disks distort, tidal tails of stars and gas are drawn out. Gas clouds collide, compress, and trigger starbursts. The two central black holes are spiral toward each other. Eventually, they merge, radiating a burst of gravitational waves. Form a single, even more massive central black hole in the remnant galaxy. The final galaxy is likely an elliptical or lenticular system. No neat spiral arms, more random stellar orbits. Solar system, very unlikely to collide with anything. Most likely just ends up in a new orbit in the merged galaxy, with a very different night sky. 9. The human meaning part. The narration also leans into philosophy and feelings. Quiet power. The black hole is hugely powerful, but mostly silent. Power doesn't have to be loud. Indirect knowledge, we know it exists from its effects, not by seeing it directly, a parallel to many unseen influences in life. Timescales, processes around it run on millions, billions of years, a reminder that the universe is unhurried. Cycles, black holes and galaxies have active phases and quiet phases, activity and rest as natural rhythms. Limits of knowledge, the event horizon marks a fundamental boundary of what can be known, accepting some mysteries. perspective, our lives are tiny compared to galactic timescales, yet we can still understand and model these distant things, small but capable. 10. If you're using this to fall asleep. If you want a simple, sleepy mental image to carry, a huge spiral galaxy hanging in the dark, slowly turning over hundreds of millions of years. At its center, a completely silent, invisible weight, calmly holding millions of stars in smooth orbits, barely feeding, just being there, unchanged by whether anyone is watching. About that black hole-like vortex inside the sun claim, reality check. JWST doesn't look at the sun at all. It's an infrared telescope designed to look at faint, cold, distant things, early galaxies, exoplanets, nebulae, etc. Pointing it anywhere near the sun would literally damage it. Solar science is done by other missions, like SOHO, Solar and Heliospheric Observation, SDO, Solar Dynamics Observation, Solar Orbiter. These do see vortices and dark regions, sunspots, coronal holes, but those are magnetic and thermal structures, not black holes or anything close. There are no reputable NASA, ESA, or peer-reviewed papers seeing anything like black hole-like vortex inside the sun. The phrase only shows up in clickbait videos and fringe sites, not in real solar physics literature or mainstream news. So scientifically, there is no black hole, mini black hole, nor black hole-like object inside the sun. The sun is a normal G-type main sequence star with a hot plasma interior and well-understood structure. When people say vortex near the sun, they usually mean twisted magnetic field lines, rotating plasma flows in the corona or photosphere, or a poetic way to describe frame dragging near spinning black holes, totally different objects. 2. What the transcript is actually doing. The transcript you pasted isn't really about James Webb or any real new discovery. It's a patchwork of speculative what-if segments. Roughly, it runs through, what if a small black hole hit the sun? Explains stellar black holes and tidal disruption. Dramatizes how unlikely but catastrophic a close encounter would be. The odds of a rogue black hole actually passing through our solar system are tiny. What if the sun suddenly went dark or vanished? Talks about ecosystems collapsing, temperature dropping, oceans freezing, humanity hiding in bunkers. Real physics, the sun can't just switch off or disappear. Stellar evolution is slow and well modeled. Why planets are round, and what if they were cubes or triangles? Introduces gravity and hydrostatic equilibrium as reasons planets become nearly spherical. Imagines crazy climates and gravity on non-spherical planets. Fun thought experiment, not physically stable long-term. Black holes versus white holes. Explains white holes as a speculative time reverse of black holes based on mathematical extensions of GR. In mainstream physics, we have observational evidence for black holes, but none for white holes. They're theoretical. Living in Saturn's rings. Uses the ring structure A, B, C, D, E, F, G, and the idea of building stations on chunks of ice and rock. Real world, the rings are very sparse, high-speed debris. Long-term settlement there would be brutally hard. Living on a rogue planet. Talks about no star, using geothermal energy, underground oceans, artificial biospheres. This part is actually close to current astrobiology speculation. Subsurface life on rogue planets is considered possible in some models. Swapping the sun and the moon. Correctly notes, putting the sun at lunar distance would obliterate Earth. Putting Earth farther from the sun would freeze it. then imagines if we somehow survive with advanced tech. That's firmly in sci-fi territory. So the pattern is real physics concepts, gravity, tides, stellar evolution, black holes, blended with extreme, often impossible what-ifs for entertainment. If you want, we can go deeper. If you tell me what you actually care about here, I can zoom in. Want a clean debunk of the JWST saw a vortex in the sun claim? Want help separating fact versus fiction for any one of those scenarios, black hole and sun, white holes, rogue planets, Saturn's rings, etc.? Want this turned into exam-style notes or a quick study sheet on the real astrophysics behind the dramatics? Pick a section, and I'll treat it seriously and strip out the clickbait. 1. Things the video gets basically right. Our sun really is a minority type of star. Most stars in the Milky Way are red dwarfs, small, cool, M-type stars. Estimates are around 70 to 75% of all stars. G-type yellow dwarfs like the sun are closer to 7 to 10% of the population, so about 10% is fair. G-type stars are good, long-lived, stable energy sources, so they're considered decent candidates for life-bearing systems. Our planetary layout is unusual compared to many known systems. From Kepler and other surveys, we've learned that around sun-like stars, the most commonly detected planets within 1 AU are super-Earths and sub-Neptunes, roughly 1.5 to 4 Earth radii. Those appear around 30 to 50% of sun-like stars. Our system has none of those, just 4 small rocky planets and then a big jump to gas ice giants. That's genuinely odd compared with the exoplanet zoo we've found so far. Hot Jupiters, Jupiter mass very close to their star, are indeed rare, around 1% of stars. We don't have one, which likely helped our inner system stay calm. So, our solar system doesn't look like the typical Kepler system is basically true. Planets to planets, migration, and grand attack style ideas. It's standard now that giant planets migrate through the protoplanetary disk instead of forming exactly where we see them now. One influential scenario, the grand attack, has Jupiter moving inward, then being pulled back outward when Saturn forms and locks into resonance with it, reshaping the inner system. This is indeed a serious, though still debated model. The idea that this cleared some material and affected what planets could form inside is reasonable. Asteroid belt and late heavy bombardment. The asteroid belt really is failed planet territory. Jupiter's gravity kept the material from coalescing into a planet. The late heavy bombardment, a spike in impacts about 4 billion years ago, may have been triggered by a rearrangement of the giant planets and might have delivered water or organics to Earth. This is still debated, but it's a mainstream idea, not pure fantasy. Earth's moon is a bit of a freak. The leading model is indeed a giant impact with a Mars-sized body early in Earth's history. Our moon is very large relative to Earth compared with other planet-moon systems. Some astronomers do call it a near double planet. The moon does help stabilize Earth's axial tilt and drive significant tides, which probably matter for climate stability and early life. How common Earth-moon-like systems are around other stars? We honestly don't know yet. Exomoons are very hard to detect. The sun is single. Many stars aren't. For sun-like FGK stars, about 46% are in multiple systems, so a lot of stars are in binaries and multiples is right, but most individual systems are actually single. Planet formation in tight binaries can be disrupted, so being in a single star system probably does help with long-term orbital stability. Galactic habitable zone. We do seem to be in a relatively quiet part of the galaxy, between spiral arms and far from the central black hole and the worst supernova action. The idea of a galactic habitable zone is real, though still debated and not sharply defined. So the core message that our system is somewhat unusual and that multiple nice features line up is broadly fair. 2. Where the video overreaches. Ordered systems like ours are less than 1%, and we're basically unique. The video uses a classification, ordered, anti-ordered, mixed, or similar, and says ours is the rarest type and less than 1% of systems look like this. Reality check. Studies do find that many multi-planet systems have planets with similar sizes and regular spacing, peas in a pod pattern. But most observed systems are very different regimes. Close-in planets, less than 0.5 AU, detected by Kepler. We almost never see full systems out to distances where our Jupiters and Neptunes live. They're too hard to detect with current methods. So any precise percentage, like less than 1% of systems are ordered like ours, is model-dependent and not solid. Right now, the honest answer is we don't know how common solar system-like architectures are, because we mostly see just the inner few planets of other systems. No other system like ours among 900-plus multi-planet systems. True in a trivial sense. No exoplanet system we've measured is a carbon copy of ours, but that doesn't mean we're one of a kind. Detection is strongly biased towards big planets, close orbits, short periods. You need multiple transits or years of radial velocity data to confirm distant planets. So claims like we may be almost impossible to reproduce are philosophical flavor, not a scientific conclusion. Heavy fine-tuning talk. The end of the transcript gets very florid. Acoustic environments in gas giants, plasma flows, gravitational intelligence, quantum information networks across the solar system. These bits aren't standard parts of planetary formation theory, mostly don't require ultra-narrow special values, and written to sound mystical and ultra-fine-tuned. From a mainstream astrophysics standpoint, a lot of that is poetic overlay, not established science. Sun and metallicity. The sun being slightly metal-rich, high in elements heavier than helium, is important. Metal-rich stars are more likely to host planets, especially giant ones. But calling it an anomaly that proves our system is fantastically special is too strong. It's towards the favorable end of a distribution, not some 1 in a billion outlier. 3. So how rare is our solar system really? Right now, the mainstream picture is more like 3.1. We're weird in a few clear ways. No close-in super-Earths or mini-Neptunes. These are very common within 1 AU around sun-like stars. Our system apparently skipped them. We have a cold Jupiter at 5 AU. Jupiter-like planets beyond 3 AU, cold Jupiters, are found around perhaps 5 to 10% of sun-like stars. The combo no super-Earths inside and one cold Jupiter outside appears to be uncommon, though not once in a universe, rare. Big stabilizing moon. Our moon size relative to Earth is unusual. How rare that is unknown because we basically can't see Earth-moon analogs yet. Long-term, quiet stability. Many exoplanets have more eccentric orbits than ours. Our nearly circular orbits over billions of years do suggest a relatively gentle history, at least recently. So we're probably in the somewhat atypical tail of the distribution, especially among systems around sun-like stars. But once in a galaxy masterpiece is not justified. Yet. Limits, caveats. Detection bias is huge. Earth-like planets at 1 AU and Jupiters at 5 AU are exactly the hardest to detect with our current tools. We have thousands of systems, not millions. That's good, but still small compared to the galaxy's hundreds of billions of stars. Several reviews explicitly say this is still an open question. The solar system is definitely weird, but we cannot yet quantify how rare it is. Future missions, example ESA's Plato, NASA's Rowan Space Telescope, long baseline radial velocity, and direct imaging surveys are specifically aimed at answering how many systems actually look broadly like ours, with small inner rocky planets and distant cold giants. We just don't have that census yet. 4. A good way to hold this in your mind? A balanced take might be, our solar system is not average among the systems we've seen so far. Its lack of close-in big planets and its nice cold Jupiter plus big moon combo make it interesting and somewhat unusual. It might turn out that these properties are important for long-term habitability, but that's still being studied. Calling it almost impossible or unique in the galaxy is poetic and speculative, not an evidence-based statement. Right now, the honest scientist's answer is, we look special in some ways, but we don't yet know how special. So you can enjoy the awe the video leans into. Our home system really is pretty amazing. Just keep a little mental asterisk that says, cool story, but the statistics are not settled yet. 1. Things the video gets basically right. Our sun really is a minority type of star. Most stars in the Milky Way are red dwarfs, small, cool, M-type stars. Estimates are around 70 to 75% of all stars. G-type yellow dwarfs, like the sun, are closer to 7 to 10% of the population. So about 10% is fair. G-type stars are good, long-lived, stable energy sources, so they're considered decent candidates for life-bearing systems. Our planetary layout is unusual compared to many known systems. From Kepler and other surveys, we've learned that around sun-like stars, the most commonly detected planets within 1 AU are super-Earths and sub-Neptunes, roughly 1.5 to 4 Earth radii. Those appear around 30 to 50% of sun-like stars. Our system has none of those, just 4 small rocky planets, and then a big jump to gas/ice giants. That's genuinely odd compared with the exoplanet zoo we found so far. Hot Jupiters are indeed rare, around 1% of stars, but easy to detect. We don't have one, which likely helped our inner system stay calm. So our solar system doesn't look like the typical Kepler system is basically true. Migration and grand tax style ideas. It's standard now that giant planets migrate through the protoplanetary disk instead of forming exactly where we see them now. One influential scenario, the grand tack, has Jupiter moving inward, then being pulled back outward when Saturn forms and locks into resonance with it, reshaping the inner system. This is indeed a serious, though still debated model. The idea that this cleared some material and affected what planets could form inside is reasonable. Asteroid belt and late heavy bombardment. The asteroid belt really is a failed planet territory. Jupiter's gravity kept the material from coalescing into a planet. The late heavy bombardment, a spike in impacts about 4 billion years ago, may have been triggered by a rearrangement of the giant planets and might have delivered water and organics to Earth. This is still debated, but it's a mainstream idea, not pure fantasy. Moon is a bit of a freak. The leading model is indeed a giant impact with a Mars-sized body early in Earth's history. Our moon is very large relative to Earth compared with other planet-moon systems. Some astronomers do call it a near double planet. The moon does help stabilize Earth's axial tilt and drive significant tides, which probably matter for climate stability and early life. How common Earth-moon-like systems are around other stars? We honestly don't know yet. Exomoons are very hard to detect. Sun is single. Many stars aren't. For sun-like FGK stars, about 46% are in multiple systems. So a lot of stars are in binaries or multiples is right, but most individual systems are actually single. Planet formation in tight binaries can be disrupted, so being in a single star system probably does help with long-term orbital stability. Galactic habitable zone.
We do seem to be in a relatively quiet part of the galaxy, between spiral arms and far from the central black hole and the worst supernova action. The idea of a galactic habitable zone is real, though still debated and not sharply defined. So, the core message that our system is somewhat unusual and that multiple nice features line up is broadly fair. 2. Where the video overreaches. Ordered systems like ours are less than 1% and we're basically unique. The video uses a classification, ordered, anti-ordered, mixed, or similar, and says ours is the rarest type and less than 1% of systems look like this. Reality check? Studies do find that many multi-planet systems have planets with similar sizes and regular spacing, peas in a pod pattern. But most observed systems are very different regimes, close-in planets, less than 0.5 AU, detected by Kepler. We almost never see full systems out to distances where our Jupiters and Neptunes live. They're too hard to detect with current methods. So, any precise percentage, like less than 1% of systems are ordered like ours, is model-dependent and not solid. Right now, the honest answer is we don't know how common solar system-like architectures are because we mostly see just the inner few planets of other systems. No other system like ours among 900 multi-planet systems. True in a trivial sense, no exoplanet system we've measured is a carbon copy of ours, but that doesn't mean we're one of a kind. Detection is strongly biased towards big planets, close-in orbits, short periods. You need multiple transits or years of radial velocity data to confirm distant planets. So if aliens looked at us with Kepler-like tech from far away, they might only see Venus and maybe Earth and maybe Jupiter's tug, not the full 8-planet architecture. So claims like we may be nearly impossible to reproduce are philosophical flavor, not a scientific conclusion. Heavy fine-tuning talk. The end of the transcript gets very florid. Acoustic environments and gas giants, plasma flows, gravitational intelligence, quantum information networks across the solar system. These bits aren't standard parts of planetary formation theory, mostly don't require ultra-narrow special values, and are written to sound mystical and ultra-fine-tuned. From a mainstream astrophysics standpoint, a lot of that is poetic overlay, not established science. Sun and metallicity. The sun being slightly metal-rich, high in elements heavier than helium, is important. Metal-rich stars are more likely to host planets, especially giant ones. But calling it an anomaly that proves our system is fantastically special is too strong. It's toward the favorable end of a distribution, not some 1 in a billion outlier. So, how rare is our solar system really? Right now, the mainstream picture is more like 3.1. We're weird in a few clear ways. No close-in super-Earths or mini-Neptunes. These are very common within 1 AU around Sun-like stars. Our system apparently skipped them. We have a cold Jupiter at 5 AU. Jupiter-like planets beyond 3 AU, cold Jupiters, are found around perhaps 5 to 10% of Sun-like stars. The combo no super-Earths inside plus 1 cold Jupiter outside appears uncommon, though not once in a universe rare. Big stabilizing moon. Our moon's size relative to Earth is unusual. How rare that is unknown because we basically can't see Earth-moon-like analogs yet. Long-term quiet stability. Many exoplanets have more eccentric orbits than ours. Our nearly circular orbits over billions of years do suggest a relatively gentle history, at least recently. So we're probably in the somewhat atypical tail of the distribution, especially among systems around sun-like stars. But once-in-a-galaxy masterpiece is not justified yet. Limits, caveats. Detection bias is huge. Earth-like planets at 1 AU and Jupiters at 5 AU are exactly the hardest to detect with our current tools. We have thousands of systems, not millions. That's good, but still small compared to the galaxy's hundreds of billions of stars. Several reviews explicitly say this is still an open question. The solar system is definitely weird, but we cannot yet quantify how rare it is. Future missions, example, ESA's Plato, NASA's Roman Space Telescope, long baseline radio velocity and direct imaging surveys are specifically aimed at answering how many systems actually look broadly like ours, with small inner rocky planets and distant cold giants. We just don't have that census yet. A good way to hold this in your mind. A balanced take might be, our solar system is not average among the systems we've seen so far. Its lack of close-in big planets and its nice cold Jupiter plus big moon combo make it interesting and somewhat unusual. It might turn out that these properties are important for long-term habitability, but that's still being studied. Calling it almost impossible or unique in the galaxy is poetic and speculative, not an evidence-based statement. Right now, the honest scientist's answer is, we look special in some ways, but we don't yet know how special. So you can enjoy the awe the video leans into. Our home system really is pretty amazing. Just keep a little mental asterisk that says, cool story, but the statistics are not settled yet.
No part of that JWST just detected a black hole-like vortex inside the sun claim is real astronomy. It's just clickbait wrapped around a bunch of sci-fi what-if stories. Here's the key reality check tied to parts of the transcript you pasted. 1. Can JWST even look at the sun? No. By design, the James Webb Space Telescope never points at the sun. Webb sits at the Sun-Earth L2 point and must keep the sun, Earth, and moon all on the same side of its sun shield so its optics stay extremely cold. It always points away from the sun. It's built for faint infrared targets, distant galaxies, exoplanets, cool stars, Uranus or Neptune, etc., not super bright objects like the sun. So JWST literally cannot take an image inside the sun, let alone discover a black hole-like vortex there. Any video claiming that is misrepresenting what Webb can do. If we discovered some new vortex or odd structure on the sun, it would come from solar missions, like NASA's Solar Dynamics Observatory, SOHO, Solar Orbiter, or Parker Solar Probe, not JWST. 2. Black hole-like vortex in the sun? Nothing like that has been reported in the scientific literature or by space agencies. What does get misreported are sunspots, dark, cooler regions on the sun's surface caused by concentrated magnetic fields. Coronal holes, large, darker patches in ultraviolet or X-ray images where the sun's magnetic field opens and allows solar wind to escape more easily. They can look like holes in some images and are often hyped online as giant holes or black holes in the sun. These are normal magnetic features, not black holes, and not literal holes going inside the sun. There is no evidence of a black hole inside the sun, a vortex in the solar interior behaving like a black hole, JWST just detecting such a thing. Those are made-up narrative elements. 3. What the transcript actually talks about. If you look at your transcript, after the dramatic opening, it mostly does generic science fantasy what-if scenarios. What if a stellar mass black hole hit the sun? What if the sun turned off? What if planets were cubes? What if white holes existed and fought black holes? What if we lived on Saturn's rings or a rogue planet? What if the sun and moon swapped places? Those are thought experiments for entertainment. Some bits are loosely based on real physics, like how black holes form, light taking 8 minutes from sun to Earth, but most of the specifics are exaggerated or outright wrong. Rogue black hole eating the sun? Black holes that could come near us are extremely rare. The nearest known, Gaia BH1, is 1,560 light-years away and about 10 solar masses. That's very far and not heading for us. The sun suddenly going dark?
The sun can't just switch off instantaneously. Stellar evolution doesn't work like a light switch. It will gradually brighten over billions of years, then eventually become a red giant and white dwarf. White holes, these are purely theoretical solutions of Einstein's equations. There is no observational evidence that any white hole actually exists. Humans and giant tardigrades on a frozen, sunless Earth? Fun sci-fi, not current biology or climate science. So the title suggests a brand new, dramatic JWST discovery, but the content never actually shows data, quotes a paper, or even explains what JWST supposedly saw. That's a big red flag. 4. Is anything in there at least roughly right? Yes, a few points are in the right ballpark. Black holes come in stellar, intermediate, and supermassive mass ranges, with stellar mass ones forming from massive star collapse. A close encounter between a black hole and the sun would be catastrophic for the solar system, but the probability is absurdly tiny. If the sun somehow stopped shining, Earth really would start cooling rapidly. Photosynthesis would fail, and complex life would be in deep trouble within weeks to months. But these are generic facts you can find in any astronomy book. They're not evidence that JWST just detected anything inside the sun. 5. How to sanity check videos like this? A few quick tests you can use next time. Instrument check. Ask, is this telescope even capable of observing this object? JWST? No, son. Source check. Is there a link to a NASA ESA press release or peer-reviewed paper? Big discoveries always have one. Terminology. Phrases like black hole like vortex, time reversal of a black hole, etc., without math or references are usually storytelling, not scientific language. Headline versus body. If the title screams, "No discovery," but the video just talks about generic facts and wild hypotheticals, it's clickbait. If you'd like, I can point you to some real recent JWST discoveries or break down any one of the what-if scenarios from the transcript and rebuild it with accurate physics.
What 3-Eye Atlas actually is. 3-Eye Atlas in a nutshell. It's the third confirmed interstellar object after 1-Eye Oumuamua and 2-Eye Borisov, and the second one that clearly behaves like a normal comet with a coma and tail. Discovered in July 2025 by the Atlas Survey in Hawaii. Roughly 10 to 12 kilometers, about 7 miles across, so much larger than Oumuamua and 2-Eye Borisov. The big surprise, CO2-dominated coma. Using JWST, astronomers measure the gases coming off 3-Eye Atlas and found that its coma is dominated by carbon dioxide, not water. The CO2/H2O mixing ratio is about 7 to 8, one of the highest ever seen in a comet. Typical solar system comets are water-dominated with much lower CO2 fractions. So the video's idea that CO2 is the star of the show is basically right, though erasing water is oversold. More on that below. Water is there. Radio observations using the Meerkat array in South Africa detected OH radicals, which are produced when sunlight breaks apart water molecules, the classic way we confirm water outgassing. Separate work showed 3-Eye Atlas is losing water like a fire hose as it approaches the sun, just with a very unusual composition ratio compared to other comets. Radiation-processed crust. Interstellar space bombards icy bodies with cosmic rays and high-energy particles for millions to billions of years. Lab experiments and models show these can break apart CO and other molecules and reassemble them into CO2 and more complex organics, slowly darkening and reddening the surface.
That matches what's being proposed for 3I Atlas, an outer shell whose chemistry has been heavily reworked by radiation, with more pristine ices deeper down. Color and weird surface. Optical observations show 3I Atlas has unusual color and polarization properties compared to ordinary comets, more extreme but not outside what comets can do. The idea that the surface is a radiation-hardened dark red crust saturated with CO2 is consistent with current modeling, though the exact details, thickness, texture, are still being worked out. Multi-mission observations. A whole zoo of observatories has watched this thing. Hubble, JWST, ground-based telescopes, radio arrays like Meerkat, and spacecraft near Mars, especially ESA's ExoMars Trace Gas Orbiter, not just NASA orbiters. That coordinated tracking really does help pin down its trajectory and outgassing behavior better than ground-based telescopes alone. What the video gets broadly right: CO2 burst and weird chemistry. Yes, 3I Atlas really is extremely CO2 rich compared to its water output, unlike any comet we've ever seen before. This is a genuine scientific surprise and is driving new work on how interstellar radiation reprocesses comet surfaces. Radiation reshaping the surface. The story about high-energy particles breaking molecules and reforming CO2 and complex carbon crusts is very much in line with current ideas. Researchers do think much of the outer layer has been chemically rewritten by interstellar space, not just preserved from its birth environment. Thick, processed shell hiding the interior. Models suggest interstellar comets can build up a processed crust many meters thick, which means what we see off the surface may tell us more about the journey than about the original protoplanetary disk. That's a real conceptual shift for how we interpret interstellar visitors. Meerkat detecting water fragments. The video's bit about a radio telescope picking up faint signatures from water breakdown products is accurate. Meerkat detected OH emission from 3I Atlas, confirming that water is outgassing beneath that weird surface. Lots of hype around anomalies. There has been public fuss over various anomalies of 3I Atlas, including some speculation about artificial origin. Planetary scientists have pushed back hard and emphasized that while extreme, its behavior is well within the wild diversity of comets. Where the video is misleading, overconfident, or just wrong. CO2 explosion that nearly erased the water signature. JWST did not see water vanish. It saw that CO2 dominates by a factor of about 7 to 8, which is very unusual but not no water. Other instruments like Swift and Meerkat explicitly confirm strong water loss. The water barely above background framing is dramatized. Invented or shaky spacecraft details. I can't find any credible reference to a Chinese spacecraft called TN-11 associated with 3I Atlas, or at all. All the multi-mission campaign write-ups name things like Hubble, JWST, ExoMars TGO, Mars Express, and ground-based telescopes, not TN-11. Mars missions have contributed, but the specific mix in the video, like TN-11 plus a particular set of Mars orbiters, looks partly fictional or confused. Exact crust thickness stated as fact. The video talks as if a 10+ meter crust thickness is firmly measured. In reality, this is inferred from models of heat transport, radiation processing, and outgassing behavior. It's plausible, but not a directly measured number. Dozens or hundreds of interstellar visitors per year? Future surveys, especially the Vera Rubin Observatory, are indeed expected to find more interstellar objects, but forecasts are more like dozens over the decade, that is, maybe a few per year, not hundreds every year. Planetary Defense Revolution language. Using multiple spacecraft to track a fast interstellar comet is a useful test case, but framing it as a huge planetary defense breakthrough is pretty over the top. The main impact right now is on science methods, not we can now defend against rogue interstellar rocks. Tone, everything sounds unprecedented and almost impossible. 3i Atlas is definitely extreme in several ways: composition, polarization, brightness evolution. But comets as a class are incredibly messy and diverse. Planetary scientists are not so much baffled as excited by an outlier that still looks very comet-like overall. What this really means for comets and interstellar visitors. Here's the genuinely cool scientific takeaway, minus the YouTube drama. Interstellar comets carry two stories at once. Inner layers, where and how they formed around their original star. Outer layers, how billions of years of cosmic rays and radiation have resculpted their chemistry and color. Surfaces might mislead us about origin. 3i Atlas shows that by the time an object has wandered between the stars and then into our system, its surface can be dominated by radiation products like extra CO2 rather than pristine ices. We have to disentangle birth chemistry from journey chemistry. We need better tools to see past the crust. Future missions and telescopes will have to watch how gases seep through process layers as the object heats up. Compare many interstellar objects to see patterns. Maybe someday send a sample return or close flyby mission to directly probe beneath the surface. 3i Atlas is weird, but it's still a comet. Multiple lines of evidence: water, CO2, dust, tail, non-gravitational acceleration, brightness evolution, all point to very odd comet, not anything artificial or magical. If you'd like, next we can translate all this into a super simple kid-level explanation, or go the other way and dive into the actual JWST spectra and what CO2/H2O 7.6 really implies for its thermal history. Either way, 3i Atlas is genuinely fascinating, just not quite as sci-fi as the video makes it sound.
Over the past few hundred years, humanity has seen an unprecedented explosion in science and technology, a rate of progress far beyond most of our 195,000 to 300,000 years of existence. This naturally raises big questions. What might we achieve in the next 100, 1,000, or even millions to billions of years? Are we alone in the universe? Are we among the most advanced civilizations, or actually one of the least developed? As our knowledge of the cosmos grows, we're forced to confront our place in it. The Kardashev scale, ranking civilizations by energy. To compare the level of different civilizations, scientists often refer to the Kardashev scale, proposed in 1963 by Russian physicist Nikolai Kardashev. It classifies civilizations by how much energy they can harness and control. Originally, it had three main types. Type 1, planetary civilization. A Type 1 civilization can harness all the energy resources of its home planet: solar, wind, hydro, geothermal, nuclear, fossil fuels, and even other possible forms of energy we don't yet know. Humanity has not reached Type 1 yet. As physicist Michio Kaku notes, managing a planet's energy isn't just about extracting it, but controlling and regulating it, including the ability to control weather, prevent natural disasters like earthquakes, hurricanes, and tsunamis. We are far from that. According to estimates, humanity is around Type 0.7 and might reach Type 1 in about 100, 200 years if we don't self-destruct first. Type 2, stellar civilization.
A Type 2 civilization can use all the energy output of its star. To imagine this, note that in just 1 second, the sun emits enough energy to power human civilization for thousands of years. One famous idea is the Dyson sphere, proposed by physicist Freeman Dyson, a gigantic structure or swarm surrounding a star to capture most or all of its radiant energy. A Type 2 civilization could build something like that around its star. Type 3, Galactic civilization. A Type 3 civilization can harness the energy of an entire galaxy. That would require travel at or near the speed of light, or something even more exotic. Technology far beyond our current imagination. The ability to manipulate phenomena on galactic scales, possibly even engineering supernovae or interacting with supermassive black holes. Later thinkers extended the Kardashev scale even further. Type 4 uses the energy of the entire universe, controls space and time on cosmic scales, manipulates dark matter and dark energy, could appear godlike from our perspective. Type 5 can move across parallel universes, create new forms of life, and use effectively infinite energy, sometimes compared to gods in a metaphysical sense. Type 6 exists outside space and time, creating and destroying universes and multiverses. If such beings exist, we might not even be able to detect them. Type 7 controls both space and time completely, seeds new universes, and has essentially achieved immortality. These higher types are speculative, more about stretching human imagination than strict science, but they highlight how low on the ladder we currently are. The Fermi paradox. Where is everybody? Given the universe is enormous. There are 10 to the 22 to 10 to the 24 stars, a 1 with 22 to 24 zeros. For every grain of sand on Earth's beaches, there are roughly 10,000 stars out there. Our galaxy alone likely has about 100 billion stars. If even a small fraction of these stars have Earth-like planets, an even smaller fraction of those develop intelligent life and advanced technology, then there should be huge numbers of advanced civilizations in the observable universe, on the order of 10 to the 16. Focusing just on the Milky Way, 100 billion stars. That's a billion Earth-like planets, so maybe 100,000 intelligent civilizations, even with conservative percentages. If that's true, and even a small fraction of them broadcast radio or other signals, then our radio telescopes, like the SETI projects, should be flooded with signals. But we hear nothing. Silence. This is the Fermi paradox, named after physicist Fermi Frener, who famously asked, "Where are they?" If advanced civilizations are common, why don't we see any obvious signs of them? No Dyson spheres, no colonized galaxy, no detectable signals. The Great Filter. Why we might be rare or doomed. One influential idea to explain this is the Great Filter, proposed by Robin Hanson in the 1990s. The idea is, to go from lifeless planet to interstellar civilization, life must pass a series of extremely improbable steps. At least one of those steps is so unlikely that almost no species makes it past it. That's the Great Filter. Possible crucial steps include a habitable planet forms in the right zone around a star. Life arises from non-living matter, a biogenesis. Life develops self-replicating systems like DNA or RNA. Single-celled organisms, prokaryotes, evolve into more complex eukaryote cells. Multicellular organisms appear. Sexual reproduction evolves, dramatically boosting genetic diversity. Complex tool-using intelligence evolves. A technological civilization arises capable of space flight and large-scale engineering. That civilization survives long-term, colonizes other systems, and doesn't destroy itself. The great filter could be behind us, around us, or even ahead of us. 1. The great filter is behind us. Best case for humanity. In this scenario, one or more early steps were unbelievably unlikely. For example, the origin of life itself might be almost impossible. The jump from simple cells to complex cells may be insanely rare. Conditions like those on Earth, our moon, our orbit, our geology, might be extraordinarily unique. If that's so, that explains why we don't see other advanced civilizations. They almost never got this far. We're one of the lucky few. That would mean humanity is special. Not because we're the center of the universe, but because we're a rare success story in a universe mostly filled with dead planets or simple microbes. That would mean humanity is special, not because we're the center of the universe, but because we're a rare success story in a universe mostly filled with dead planets or simple microbes. 2. The great filter is now, or we're among the very first. Maybe the universe only recently became calm enough for advanced life to appear and persist. Early in cosmic history, gamma-ray bursts, intense radiation, and frequent cataclysms might have repeatedly sterilized planets. Only now has the universe cooled and stabilized enough for complex life to appear and persist. In this view, we and a few other intelligent species might be among the very first intelligent species. So it's simply too early for Type 2 or Type 3 civilizations to be common. The galaxy isn't full yet. 3. The great filter is ahead of us. This is the worst-case scenario. The steps up to our current level are common. Many civilizations reach roughly our technological stage, but most are then destroyed by either their own technology, nuclear war, runaway AI, nanotech, or engineered pandemics, or external cosmic disasters like asteroid impacts, nearby supernovae, or gamma-ray bursts. If this is true, then civilizations tend to self-destruct or get wiped out before they can spread. We might be approaching that same wall. Other explanations for the Fermi paradox. Scientists and philosophers have suggested